Time travel, a concept ingrained in human imagination for centuries, revolves around the notion of journeying to either the past or the future. Before delving deeper, let's establish the groundwork. According to Einstein's theory of relativity, our perception of the now is in constant flux, continuously evolving alongside time. Time's passage is discerned through our accumulation of memories and awareness of past and present events. This accumulation constructs a sense of continuity along our timeline. An experience intrinsically linked to human consciousness and the structure of our brains. Einstein himself, a firm believer in physics, contended that the distinction between past, present, and future is a persistently stubborn illusion. This notion raises the question, could our comprehension of time merely be an illusion, thereby offering a potential avenue to disrupt the natural progression of the universe? In this exploration, we ponder the theoretical possibility of disrupting the natural flow of time. When people think of time travel, the common imagery involves a person traversing backward or forward in time without physical alterations to their body. However, envision a scenario where the traveler, aiming to witness their younger self from 2 decades ago, arrives as a baby themselves, an unexpected and humorous twist challenging our understanding of temporal flow. Conventionally, our comprehension dictates that time moves linearly, guiding us from the past to the future. Despite various interpretations, time travel typically involves accelerating into the future or journeying back into the past. This process disrupts the conventional rate of time by a specific factor, deviating from our accustomed temporal progression. Newtonian mechanics previously construed time as linear and deterministic. However, Einstein's theory of relativity revolutionized this perception, supplanting the notion of absolute time and space with the idea that time possesses subjective significance for each individual. Thus, the concept of time travel offers a thought-provoking lens through which we ponder the complexities and nuances of time itself, challenging our fundamental understanding of how the universe progresses. In the context of Einstein's theories, special relativity, SR, and general relativity, GR, time is considered as one dimension interwoven with space. SR views time as part of a dynamically curved space, while GR examines time within the realm of dynamically curved space. In this framework, the prospect of moving backward or forward in time may not be as implausible as commonly thought. It could potentially be as straightforward as traversing different points in space. Over the years, numerous hypothetical propositions regarding time travel have emerged from notable scientists. These scenarios differ significantly from the concept of a physical machine with levers and dials, akin to what H.G. Wells once proposed. Einstein's work has demonstrated that time elapses differently in diverse situations. This signifies that time progresses at varying rates for different observers, contingent upon their traveling speed. Consider the example of astronauts aboard the International Space Station, ISS, orbiting Earth at 28,000 kilometers per hour. When accounting for the interplay between GR and SR, this would result in a net time dilation effect experienced by the astronauts in contrast to an observer stationed on the planet's surface. To avoid delving into intricate specifics, it's noteworthy that the astronauts aboard the spaceship experience a time dilation effect per day. For an average crew member stationed on the ISS for 6 months, the cumulative time dilation would approximate about 5 milliseconds. In such a scenario where an astronaut has a twin, the astronaut who voyages through space encounters a lesser passage of time compared to their counterpart remaining on Earth's surface. This situation presents an intriguing concept of fast-forwarding through time, which seems fascinating, albeit being a one-way process without the option to return. Nonetheless, within the realm of the theory of relativity, certain scenarios potentially support the feasibility of time travel. In the early 20th century, scientist Kurt Gödel illustrated solutions to the field equations of general relativity, GR, describing space-time so intensely warped that it permits the formation of closed time-like curves. These unique configurations twist individual timelines, enabling paths from the present to either the past or the future. Gödel's solution posed a significant challenge to the traditional linear conception of time. Similarly, other physicists like Kip Thorne and Paul Davies have contemplated shortcuts within space-time. For instance, the utilization of wormholes, an intriguing concept analogous to Einstein's theory of general relativity, has been proposed to facilitate instantaneous spatial travel, opening up the possibility of traversing through space-time. Wormholes are theoretical constructs that purportedly connect two distinct points within space-time, effectively twisting a thread between these points, making them virtually indistinguishable. These theoretical structures bend space-time, requiring unimaginable amounts of energy for their creation. Scientific endeavors aim to simulate wormhole-like conditions by accelerating electrons to near-light speeds and colliding them in experiments conducted at particle accelerators like the Large Hadron Collider. However, the prevalent theory suggests that any formed wormhole would collapse instantly, potentially turning into a black hole unless a way to sustain it using negative energy, although theoretically possible, is currently impractical. The pursuit of time travel raises compelling questions, especially regarding practicality. When delving deeper into the causality of events, the feasibility of time travel appears close to impossible, encountering various logical hurdles. Concerning time travel, the likelihood of traveling backward in time is generally deemed much smaller than forward time travel. The discussion often revolves around temporal paradoxes, particularly those related to causal loops. These loops depict a sequence of events that circle back in time, encompassing an event as one of its own causes. The uncertainty about the true origin of events within such causal loops represents a significant challenge and a puzzling aspect when contemplating the possibility of time travel. It's one thing to inquire about the origins of a single event, delving into its underlying causes, tracing its roots, and attempting to understand what led to its occurrence. For instance, if one wished to unravel the narrative of their birth, they might explore details about their parents, their meeting, even extend their inquiry to encompass information about their grandparents or broader facts about human existence. However, this line of inquiry often leads to a contemplation of the evolution of our place in the universe, attempting to trace the chain of causes and effects backward infinitely. Yet, when one tries to discern the ultimate source of this entire chain, they reach a perplexing impasse, a juncture where the question of where the whole sequence originates becomes inexplicable. In the realm of standard Big Bang cosmology, it's theorized that the Big Bang doesn't mark the initial event in a sequence, but rather signifies the inception of time itself. Stephen Hawking famously remarked that the inquiry into what existed before the Big Bang is rendered meaningless because there's no definitive answer. It's akin to pondering what lies north of the North Pole, a concept without a reasonable response. Indeed, the fundamental impossibility of witnessing the origins of events with our own eyes poses a significant limitation. The prospect of experiencing and traversing between distinct timelines, let alone altering past events for the sake of shaping a different future, seems beyond our grasp. This comprehension stands as our current best understanding of the workings of time, an understanding that aligns with our perception of how the universe operates. Space and time are intricately linked, forming an inseparable connection dictated by the laws of physics within our universe. The way they intertwine serves as an expression of their interrelationship and how they mutually influence each other, shaping the fabric of reality as we comprehend it. If you found this video informative, make sure to subscribe to our channel for more content.